I guess too many video I still not yet uploaded to your to the YouTube and to your e-learning. Have to fill in the any form before exam. Oh, it is not your course. It's okay. Let me continue here. Yesterday we take a look into tree, the basic tree before you can go to the infix and postfix. When you were given with the equation or arithmetic expression, you need to come out and know how to draw a tree, because the tree later on will be become your left, right, and parents. Okay, like this will be your right, left, sorry. This will be your left and this will be your right. And here will be become your parents. So it's depend on whether you are doing the infix or postfix. If you are doing an infix, you're going to do left parents, right. So your infix from this expression, it will become A multiply with B. Similar. But when you are doing a postfix, you're going to do left, right, parents, isn't it? So your postfix will be equal to AB multiply. Okay, this is the given equation or arithmetic, your arithmetic expression. Then you come out with these three. You need to convert to infix or even a postfix. Let's say we try another one more things. This is the normal equation, and from this we can come up with this three. Okay, by using this tree, where is our left? Here will be our left. We do infix first. Left, and then parents, right. Okay, this is our first. And this one, A multiply with B. And this one will be our left now. This will be our left. Did I open my... Okay. This will become our left. So, this is our left. And we do left parents. Left. This is our left. Parents and right. This is our right. This is in terms of infix. How about our postfix? We're going to do left, right, parents. So you will get left, right, parents. So this one now will become a new left. This will become a new left, and you're going to do left, right, parents again. So this left, and you're going to have right and your parents. So this will be your postfix. So you can see it can be different between infix and postfix. You can try another. So here, yesterday we already looked into how we can get infix, how we can get also postfix. Okay, after that, yesterday we take a look into a RPN, which is reverse Polish notation. What is the purpose of RPN? You were given with the postfix or the infix, you need to come out with the expression, with the equation. So it is a reverse way. Now you were given with the infix. So from okay, reverse Polish notation, you were given with the post. Okay, this one, for this reverse Polish notation, it mentioned this is your postfix order. And postfix order. Which one is the answer? The question is slightly tricky. Okay, you were given with the expression 3. You know that how you can come up with the infix, how you can come up with your postfix. Let's say we have, okay, we have the expressions. We have left, parents, right. So we get 1. And this is become our left now. Left, parents, right. This will become our right now. This is our left. This is left and this is right. This is parent. Okay? From here, you're going to solve inside with similar because now you are doing the infix. So, left, parents, right. Where is your right? This is your right. This is your left. And this is your parent. Now here, okay, I delete this. Now this is your left. This is your parents. And this will become your right. For another one more time. And inside this right, you're going to follow another one more time, the infix. You're going to do this one again. Inside this right, you're going to start also left, parents, right. So this will be left, this will be parents, this will be right. And this will be a right for this left. This is parent. And the whole of this will be a right and this will be a left. This is parents. Okay, so you need to do slowly, step by step. Now you done the infix. So you need to try to come up with your postfix. After you done all of this, then we're going to look into the RPN, okay? Now this one is just for us to come out back with our postfix and infix. For postfix, we have left, right, parents, left, right, parents, continues. So now where is our left? This is our left. Left, this, the whole thing here will become our right. Sorry, not yet. Okay, this will become my right. This will become my right because my parent is here on top of this only. So I cannot make the whole. Because the whole here, I got another parents. Okay? That's why for this parent, I have left and right. For this parent, this is my left, this is my right. Okay? That's why I cannot include all to be my right. Okay, now I have left, right, parents. Left, right, parents. So I draw postfix equal to 1, 5 plus. This is one thing. Now it's become my left. So for this one, I can see this is my left. I have another parents here. Left, parents. And I can see that inside my parents, I have another many solution also here. I can make it as a right. This is not a small, this is a the biggest tree for our parent. That's why we can divide it to the left and to the right. And from here, it will become our left. This will become our right. So left, and we're going to do our right solution. Left, already done here. And now we're going to go to the right. This is our right first at our it. And now it's become left. And you can see there is another right. So here will become your right. And this one will become the left, and this one will become a right. So from all of this, you do left, right, parents later on, because you cannot see, you can see that there is another right there, because this is a parenting that you have in a big tree here. So you have another right, right, and then it will be parents. Left, right, parents. What happened? Okay, this one is just for you to recap what you have done here. Now you're going to go for RPN. So it gives you the example of the infix just now, and also the postfix, just for you to see that you're going to get a similar result. You're going to get a similar result. Yesterday also we take a look into the infix one, but postfix I said is slightly tricky. Then we're going to see today. So for infix, this one, you can solve one by one. If you were given only with this solution, this one is not given. So you need to draw it first, like this will become your left, and then you have another parents, and this will become your right, and you solve this. Of course, you're going to get this three. And you solve one by one. You can solve this, you can solve this. After that, you solve these two, and this can be solved. Normal mathematics. Okay, this one will become 6. This one become 3. So you get 6 and 3 here. 8 minus 3 become 5. So you get 6 multiply 5 equal to 13. Although you are doing infix, your postfix order, you can see it is not similar, but you will get the similar answer later on with the step push and pop. Okay, let's say you were given just now for this, okay, you were given with the postfix. This is our postfix. How we going to solve it, and we will get a similar solution for our 30 here. Infix and postfix should get a similar answer. Similar also at the beginnings of the equation. When the equation first is not given. So if you were having an equation or the first expression, it will be getting the similar answer also. So now, the final answer should be 30. So you can try to look into the flowchart here, how basically you're going to do. This is the step. Okay. First of all, you're going to do a pointer like this, because you will start from the left, normal reading. So you're going to point here. 1. If you found number or digit, you're going to do a push. If you meet or found parents, or we can call this as arithmetic. Arithmetic. So it will be a pop. Okay, this is the rules that you need to remember. So you're going to go one by one. Here will be push, because you meet a number. So this is your empty stack here. You're going to push first in, last out. Philo, isn't it? Philo, right? Here, LIFO, last in, first out. Similar lah, okay. I do a first in, last out, but basically similar, okay. Last in, first out. Okay, what is the meaning by this? Because, okay, you can see this is the first one that will be pushed inside your stack. You're going to push inside your stack, isn't it? And then your pointer will be changing to here. You still meet the number. Then you're going to do what again? Push again. Then you have 5. After that, you're going to meet apa ni? Parents, or might be equation for you to add, subtraction, multiplication. So this one, you're going to do what? Pop. So you can see this is last one that coming in, but it will be a coming out first. Last in, first out. LIFO, okay? LIFO for this. This is the last one that coming in, but this is the first that will coming out by doing a pop. Okay, so here we are at the first one. We pointing here. We're going to push our digit 1. We go to the pointing number 2. We point here. This still digit. This is the number. Then we're going to do what? Push again. So push to your stack. Basically, this one is similar stack, okay? Then you go to this third one. You meet adding here. So you're going to do what? Pop. So pop, what happened is you're going to take this out. 5, you're going to take this out, and you're going to add this and take another one coming out. This one will be coming out first, okay? Then you're going to add here. So you can see here, you will bring this pop. This one will be going out first and following the second, and these two will be adding together. So you will get the total of 6. By doing the parents here, pop, you're going to do adding here first. And where this 6 will be go? Is it you're going to ignore? Cannot. You're going to take this value and push back into your stack. Okay, so you're going to push back into your stack. That's why after you find and meet the adding here parents, then you're going to get, remove here, it's going to have 6 now. You have 6, 8, 4, 1, minus x, which is totally similar from above. But the initial one is already done for this part. Push, push, pop. Then you solve this solution first. Then you will get 6, 8, 4, 1, minus, multiply. Okay, done for this part. You go for the next slide. You can see here, you're going to continue. Just now, you point here. Now, we're going to point to next. Still number. What we're going to do? We're going to put 8 here. We go to another. What we're going to do? We're going to push again. Push, okay? Push. We meet one number, still number. What we're going to do? We're going to push also. After that, we meet subtraction. Subtraction, what we're going to do? We're going to do pop. Now, pop is only, a mathematical, only adding, multiply, subtractions, and etc. Only two numbers. That's why you will pop 2 digits from your stack. Okay, let's see one by one. You point to 8, you're going to get 8 inside your stack. You point to 4, you're going to push your 4 here. You point to 1, you're going to push your 1 inside here. And suddenly you meet the subtraction. You're going to do pop. So pop, you're going to take this out and this will be here. And you put your parents here, similar to just now. This is 5. This is 1 because 5 already come out first. And then 1 and you have the parents. Similar to our just now happened also. First, you're going to bring 1 out first. And you have the parents. And you pop another 1 value. You done this one. What will happen? You need to solve. You cannot just, okay, I already pop. So nothing happened. No, you need to solve this. This will be getting 3. So what will happen? You're going to have, just now, your stack will be having like this only, right? Because you already popped 1 and 4. So your stack currently will be look like this. You have the value of 3. What are you going to do? Ignore? No, cannot. You're going to push back into your stack. So your 3 is here now. Then you can see the differentiation. Just now when you solve this one in front, you're going to put in front because it is at this side. But when you solve this part, you can see here, when you solve this part, you need to put at this side only. Also, not going to put the 3 in front. Okay, that is the difference. Although you can see, you said that, where is your 3? Although you can see 6 add 3, just now for the previous equation, you're going to, okay, just now you did not have any value. You just push back the value of 6 inside. So it's continue. Now you solve this problem, you're going to put it here at the specific place where you solve it. Then you're going to have like this. Now your pointer will be continue, okay? You cannot go back. You cannot go back and start with 6, 8. Cannot. Because just now your pointer is already here. Where your pointer point up is here. So it is at 3. This one will be push. That's why you're going to push it. So it will continue with another pointer to the right. You meet another one, which is subtraction. Okay, because it's subtraction, what will happen? You're going to pop this 3, multiply, pop this value 8. So what you will get? 5. And what will happen? This 5, you're going to put at the side of here, here. And this one, you point here, right? So you're going to push it back to your stack. Now you're going to have, okay, this one is, you pop the 3 and 8 equal to 5. And this value 5, you're going to push back to your stack. You see here? So your pointer now, after you point here, you're going to push and it will be moving to multiply. When you meet this, what happened? You're going to do pop again. So you will pop 5 multiply pop with 6 equivalent to 30. 30 is one digit. It is not 30. Okay? This value is 30, not 3 and 0. That's why just one digit here, you're going to store this lastly at your stack. Unless this, you know that at the beginning, this will be 3 and 0, then you can assume like that. You need to solve it. But if it is just like 30, you need to take this and push back to your stack. So this is your final answer. Only one value on stack. This is a one value. And this is the final result. So there is several example you can try. But this one is not in term of numbering. So you cannot see in term of mathematical. Maybe you can also change it to be numbers. Then you can try to solve using the RPN and get the postfix evaluation, whether you get the correct answer or not. And you do it also with the infix. Jauhnya. You do also with the infix, come out with the infix and also do the postfix using RPN. Okay, any question for this one? RPN for postfix using a LIFO last in first out. Okay, if no question, we can continue with another subtopic about address. So address is very important because if you wrongly put one address, then the rest of your answer will be also wrong. Okay, about instruction set. The design of instruction set is very complex. This one you can read. Okay, there is a most important fundamental issues including operating, addressing, register, instruction format, data type. So this might be a question, then you need to know all the answer. So for this, that's why we're going to learn on addressing, we learn on register. After this, also we learn on the instruction format, about the data type and also operation. That is what we cover before we can proceed with others programming, which is much more advanced. Okay, here type of operands. You have several type of operand. Last time also we already looked into. First, this is just an overview. Assembly language built in two pieces, which is you have a opcode, you have the operands. Operands, this is the destination, this is the source. Way to get the address is R2, which is source, and put the result as at the destination. That's why yesterday we take a look into this is the operand. We have the minimum of 0 and the maximum operand that we can have 3. This is the opcode, which is operation code. What to do with the data in your ALU operation. And there will be 4 types of data. numbers, characters, logical data, and addresses. Type of operand for Pentium. Okay, this one is just for your information. You need to know about Sine Integer, how big you can have, unsigned integer, binary code, floating point, how many bits that you can have. In terms of number, it must be include the numeric data. And it is important between to have the numbers used in original mathematics and numbers stored in your computer is the letter are limited to this and this. First, they are limited to the magnitude of number represented in your machines. A limit to the precision of plotting point. So you need to know the range also. 3 types of numerical data: binary integer, binary fixed point, binary floating point, or even a decimal you can write in your program. This one is numerical data for unsigned integer. You can have 16, 32, or the maximum is 64. So this is all the example for unsigned integer range. You can also see next is signed integer. For signed integer, it's slightly different with unsigned because unsigned occupy all for the magnitude value, while for signed integer, you're going to have sign here at the first digit. The rest will become your magnitude, or even if the numbers is fractions, you know how about the format. This is sign number, but in terms of IEEE standard, you know already about single precision, double precision, how long this all is very important. This one you already go through your test 1 last time, right? And double extended precision floating point. That is in terms of number. So you can see several number. It is on a theoretical how you can write up, what you can write up to your program. About character, you can also use, normally we use a ASCII code. Or there is another code that you can use, like extended binary coded decimal interchange code EBCDIC, used in IBM mainframes. So the purpose of this is theory for you to know, okay, what is the characters that can be used in your program. Logical data. Logical data, normally each word or addresses unit, like byte, half word, and so on, words, double words, each treated as a single unit of data, which is n bit unit. And there is 2 advantages if you are using to the bit-oriented view, which is memory used efficiently and easy to manipulate. So this is the things that you need to understand and memorize. Might be for this diagram, you can just remember, okay, data I got 3 category, and that is number. Okay, number got what? Signed, unsigned, IEEE numbering. How about character, logical data, and addresses? Okay, no other than that, just a theory. and your understanding. After this, you're going to look into a program. Okay, so here in our next subtopic, before you go deeper, you need to understand also that addressing having several types, similar also with your operand. You have also immediate addressing. See, operand also have the immediate value. Direct addressing, indirect addressing. How you going to write direct addressing? Whether you want to put like this or you want to put like this in your program. So this thing is important. So you need to know which one need to draw like this, or might be adding, which one is addressing, address, and so on. This is just an overview, the issue that might rise up while you are dealing with the addressing. So here, this is the 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 6 type of addressing that you can use. And how you're going to find the value, or maybe when you were given with the program, where you're going to refer with. If your addressing is a type of immediate, so when immediate, normally it's going to give like move EAX with the value for 4000 address inside the address of here. So you're going to pick the value and put at EAX. Might be also this one is immediate address, and this one you were given with the value of A, which is this is direct, and you point to the exact addressing that you put in your program, and you find the value of your operand. Might be in this diagram you cannot understand, but later on when you look into the program, then you know, oh, this is a direct addressing. What else you have? Indirect addressing, what you're going to write. It's not showing yet. Okay, so you can see here there is several way. Only one. I give you example. Okay, this one and this one is not similar. So you need to know which one is direct, which one is indirect, and what you need you need to do when you have like this. So all of this is a symbol whereby you need to learn from here. Okay, so you have another one which is indirect. You were given with the address. In your instruction, you were given with the address. Then your address, there will be also another one inside your address. Ask you to point to go to somewhere else. And then you will get the value inside. The value of your operand, then you're going to put into your stack, right? For register, you were given with the register name, and you go to directly point to the register value, and inside your register, you have the operand value. Register indirect, how the flow? You go to the register. In this one, you have another instruction, might be the value of the register or might be the addressing. Then it's going to point to another memory to go to grab your operand value. And lastly, the displacement. The displacement, which is adding things when you have two numbers or two things here. Like here, you have the register, you add with the address. Go to your register first, and then from here, you're going to add with your address, and you're going to get the value from your memory. Okay, might be if you did not see yet, you can see all the example after this. One by one, we look into immediate addressing. For the immediate addressing, normally we were given only with direct value of the operand, which is the simplest form of addressing, which operand value is represented in instruction. So there will be a the advantage and disadvantages. So save one memory cache, but the disadvantages, the size of number is restricted. So you can go through what is the advantage and what disadvantages. For direct address, the address field content of your effective address we call as EA of the operand. Let's say from here we have the address is 4000. So your EA will pointing out to here, then this will be a value of your operand. So what is the advantage and what is the disadvantages? Here is the example when you are having direct addressing. Okay, direct addressing, you need to use this symbol, factorized symbol. When you have factorized symbol, this is what? Direct addressing. Add your register of AX. Let's say your AX value already given 10 hexadecimal. And this is the direct address. You need to go to the 1011. Go to your 1011. Let's say this is 1000, 1002, 100, blah 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 until 1011. So from here, you're going to fetch this operand value inside your memory, and you're going to add with your address register just now, 28 hexadecimal. Normally inside your memory, I already mentioned, it's all the value of hexadecimal. Sometimes it's not mentioned hash because you need to know operand. Normally for the memory, inside your memory, you need to push the value of hexadecimal. So now the final answer for your AX, because this will be also your destination. After you adding, you're going to store the value to AX. You get the 38 hexadecimal. Okay, this one is just activity. You can try to retype the following code after this. For example, 5 until 12. And try to start without debugging. And also debug F10, which is step by step. Just to see the flow and the output. But here, let's see about still direct addressing. Okay, direct addressing. Now we have different way for you to go to direct addressing. You're not putting the factorize, but from here also you were given the declaration. Oh, go to this address, which is var1. Before you come out to the code, of course this one need to store into your stack first. So first you have I will draw here, okay, so you can see. Maybe I start with 0000. Later on, if I check the value of addressing is different, so I refer to them because it's not clear mentions what is the address starting. So my var1 will have byte, which is 10. After that, I have words, array ones. This one is var1, starting here. Array 1, I have word, so it will be 2 box. Array 1, array 1 plus 1. Okay, so please remember this because this one is adding another one because this is word. Okay, this one I will pick the value of 1 0 and then 2 2. I have another one which is array 1 plus 2. I have 1 1, array 1 plus 3 0 0. I finish with array 1. After that, I have array 2. Start here, array 2. Start from here, I have the value of 23. Hexadecimal, it is not 23, it is 23. Okay, because when you convert 23 hexadecimal to decimal, is going to be different value. It is not 23. Okay, here 23 hexadecimal, array 2 plus 1, it will be 0 1. Next, I have 0 0, I have 0 0, plus 2 plus 3. I have array 2 plus 4 plus 5 plus 6 later on. Okay, here I'm going to put 3 4 0 2 0 0 0 0. So this is the first beginning. And then I'm going to go to my code. Then I will start doing my program. First, I can see it asks me to do move. I delete first here, serabut nampaknya. Okay, move this value from source to the AL. AL is register. You need to remember how long this AL can have. AL is 8 bit, isn't it? 8 bit is similar to byte. 1 byte. Okay, VAL1. So this is VAL1. So what is the value? AL equal to 10 hexadecimal. This is not 10. Okay, 10 hexadecimal. Next, I go to the second one. I will see that array 1. Where is my array 1? Array 1 start here and I need to put to my BX. Please remember BX is 16 bits or 2 bytes. Okay, 2 bytes equal to 1 word. So I have BX array 1. Array 1 is here. I will have the value of BX equal to 10. It is not yet finished because this is this is what 16 bit. I need to have another which is 22. This is 8 bit. This is 16 bit. That's why you need to complete the value. So this is hexadecimal. Next, I move to second. Oh, now I have much more bigger, which is, this one is 32 bit. 32 bit. So I have array 2. Where is my array 2? Starting from here. So ECX equal to 23 0 1 0 0 0 0. So from here you can see 1 2. This is 16. 1 2. This is another 16. Altogether will be 32 bits. Hexadecimal. So this is the value of each of that from what you're going to do just now. So you can see this is your value. when you copy this, don't ask me, doctor, why my ECX is different. Because sometimes, oh, okay, this one is cannot. This one is cannot because this one is referring directly to the address, memory here. Because later on, you're going to see like EBX, EDX is not similar to this print screen because it's depend also in your machines. Might be you have your own value. For the things that you are doing here, it is all from memory. It should be similar. Okay, like this. It should be similar. This one also should be this similar. But in front of this, it might be different from here. So don't ask me like, Doktor, kenapa? Why my answer here is different? Because sometimes your machine are doing different thing at in front of might be a process or in the register already have their own value. This is the only thing that you did from this program. That's why just only this will be need to be similar. Okay. Next, we have indirect address. Before we can proceed, can we have a break 5 minutes? Okay, thank you. We break first, okay? Okay, class, can we start? Sorry for late. Just now I did some discussion with Dr. Fuad. Indirect. Just now we already look into direct. Now we go to indirect. Okay, this one is under indirect addressing. So there will be a advantage and disadvantages. Solution for limitations of addressing range in direct addressing. To have the address of words in a memory, full length address of the operand. So this one you already look into previous slide. Look in A, which is the address given. Find address A and look they are operand for that. Okay, might be later on. Okay, here we directly given you the example. we done already the indirect. Doi, tak ada siapa jawab. Okay, this one is indirect. We already done look into the example. We done right for this part. Indirect. Not yet? Not yet. Okay, just now until direct only, right? Kenapa tak nak cakap?
Direct only.
Direct only. Okay. So here example number 6. So correct lah. Example number 6. As usual, what you need to do is you're going to have the dot data. So you're going to play around with indirect addressing after this, which is you're going to have the symbol like this. Just now, which is direct, you were putting directly to the addressing. So it is a direct one. And you can also having the symbol of this. For indirect, it is like this. Okay, so there will be a difference. Now, in a indirect. Similar also. Panjang juga ni. So, similar also, you are having array 1. Array 1 byte, 1, 0. Array 1. And you have array 2, 2, 3, 0, 1. Now we have 3, 4. This one is word, okay? 3, 4, 0, 2. A2 plus 2, A2 plus 3. A2 is array 2. We go to array 3. Array 3, D word, double word. 5, 6, 3, 4, 1, 2, 0, 0. Then we finish A3 plus 1, A3 plus 2, A3 plus 3. Okay, we done already with our stack here. Now we go to the code. First line. We know that this symbol will be indirect. Means that you need to look into this array 1. Inside your array 1, this is the address of the array 1. Maybe if it is direct, you can put like array 1. Sama je, it's going to be quite similar. But you can also put like 100 address. At this address, you're going to go to the address. Or might be it is indirect, go to here and tag the value. Okay, for this one, you have array 1. So go to the array 1 address. And you're going to tag inside that, what is the value inside? Going to have 10. So you put BL equal to 10 hexadecimal. Because this also you need to look into the size. AH high, AL low, right? So this one is similar, 8-bit, which is 1 byte. Second line, array 2. You go to the array 2. Where's array 2? Here. And this is CX. CX is 16-bit. So you have 2301. And then array 3. Array 3, starting from here, it is a 32-bit. 1, 2, 3, 4. This is the value. And lastly, you have AX. AX is array 2 plus 2. Where is array 2 plus 2? AX is 16 bits. So starting from here, you have 3402. So this is the answer. So only this will be supposedly similar. Sometime in front of this, you're going to get different. Only the red color should be similar when you run in your Visual Studio. So please try to run without debugging or step over. Now you have another one. Given 3 array with a multiple initial in the assembly, blah, blah, blah. Complete following diagram by writing the offset of memory. Assume the first offset. You can see here, last time I already mentioned you that in question, it will give you what is the starting address or offset value. But this is the example of question that can be asked in your test. So from here, you just need to complete, right? Complete the diagram here. So this one is very easy. Byte 10, word 2301, 3402. Finish word. D word 56341200. So my addressing is offset 4005. Four zero zero 10 4011 4012. So this one is just for you to store, which is easy. Without go through your module 4, you can also do this because this one you learned last time in module 2, 2 or 3. And that is how you're going to store. And after that, when you given with these kind of things, indirect or direct, you can just directly see the value inside. Might be it can change here. This one, right? Move BL 400404005. So you need to look into this address and you're going to put the value for BL. Just now we give you directly in terms of the name of your data. But if you did not given with the value of data, because you were given with the value of offset, you need to also know how to get the output. Here in terms of register addressing, this one is also quite similar, but you just using the register. The register like this. Source will be your register. Just now addressing, immediate value for operand, but these things is the register type. So just similar, this will be a source, this is the destination. Let's take a look one by one. There is no data, but it's okay, we play around with register. First of all, we have EAX 0. You need to remember EAX is 32 bits. So you're going to have 1 to 16 bit, 1 to 16 bits. Altogether 32 bits. You cannot just simply put, you can see here is 0. 0 decimal equal to 0 hexadecimal, okay? So you just put 0 here. Cannot. You're going to get your wrong answer because this is also referring to size. So for the size here, EAX, you know, you put 0 hexadecimal to your EAX. Next, you're going to do the EBX1, you put inside. But you can see you need to have another 0000. See, just to complete 32 bits. After that, you go and move to the next step. ECX sama juga, it's different. ECX will be 0000, which is you take this and put to your register. That's why you get like this. After that, move this from here, EBXU, you look into the EBX, move and store to your EAX. You replace your EAX. That's why now your EAX is 0000 to 000 hexadecimal. Just replace. But then you can see next step is, but here the thing is for you to use the register addressing. Okay, that is the way. Now it's adding. This one should add with here. So you have this value. You need to check the value of ECX. Okay, this is my value of ECX. After you add these two, ECX you're going to add to here. Means that this ECX you're going to add here. So how much you're going to have? You're going to have 5000 hexadecimal. So adding. So this will be getting a similar answer. The rest sometimes it should be different. Okay, just now it is a register directly. This one is indirect. So there is a advantage and disadvantages. How you're going to see indirect? Remember just now for addressing indirect, you have the symbol of this, isn't it? So similar also, you just replace your register. This is register, right? So this is indirect. This is register, this is indirect. This is register, is direct. Indirect. Okay, let's take a look what is the difference. We go one by one for this program. Slightly harder from previous example. Alamak, ada lagi data. So here, they're also supposedly going to having the offset value. But I think it's going to start with this value. But it's okay, it's not mentioned. Supposedly it's going to mention, okay, what value will be start for the offset. Now we have 10. I malas nak lukis sebenarnya. 10, 11, 1, 2, 1, 3. This one is array 1, array 1 plus 1. Or not here, so I just put example. We start with the offset of 40, 4004, 4005, 4006, 4007. After that, we have 2301, 34, 4002 words, okay? 4008, 4009, 4010, 4011. Okay, we done our data. Now we're going to do, as usual, the code. Move offset. This is the address of the data that's stored for this array 1. So array 1, let's say from here, the offset value, array 1 start with what? Array 1 start with this offset value. So you need to pick the offset. It's mentioned you want offset to be putting to your ESI. So your ESI will be taken the value of offset for the beginning. Again, I remind you, maybe you try to do again, then you say, how come you can get this one? Normally in question, it will be fully instruction, which is they will be given you the offset starting of what, similar to this kind of things. So you're going to start with this, then you know, okay, your array 1 will start at 4004. That's why you know, okay, array 1 is 40400. You put into your ESI. But again, remember the size. Don't forget about the size. Although you say, directly you know, okay, this is the answer. This is the answer. But you forgot about the size. You forgot just to add another 00. So your answer also will be wrong. Okay? So you can see this one is 6-bit. This one is another 16 bits. Next, we go to a next one. We have here offset also. We want to look into offset array 2. Where is array 2 start? Alamak, array 2 start 23 here. Okay, array 2 start here. So what is the offset value? Offset value is 4008. In front you add lah some more because I didn't put the full version. So the size also you need to check. So you need to tag the offset value. After that, for third line, this one is indirect. You need to go to the value of ESI. What is the value of your ESI? You go to the look your ESI value. It will become like this. Okay. If you like, okay, I like to write long, so you put here. But if you're lazy, you just put like this, which is totally similar because you know ESI is like this value. Okay. Then it is indirect, means that you need to see what is the value of operand inside that. So you go here and look inside. It is 10 hexadecimal, and again look at the size. Okay, it is 10. There is another one, EDI. See at your EDI, but the size is different already, okay? The size is different. You need to have 16-bit now. So your 6CS will be EDI starting here, 4008. You take this and this because you start here, and then after that, because you need to have 8 bit total 16 bits. So you put the answer. After that, you have another one. Another one, you move EDX. Move EDX. You got direct, which is value of your ESI. Means that, what the meaning by this? This one is indirect. You're going to look inside the value. But this one is indirect, means you want this ESI value, not the operand inside. Okay? So, what is the value of your ESI? This is the value of your ESI. You take this value inside your EDX. So now you can see what is the difference between indirect and direct. Just now, indirect, you need to look into the operand value inside. But for direct one, this value, what is the value of this? The value is 00404004. This is a value you're going to put into. Okay, now you go to next one. So please take note, do this exercise to make the differentiation between direct and indirect. And next you go to the move AL. This is indirect again, means that you're going to look into the value, right? ESI plus 1. Your ESI, you plus 1. So 4005. 4005, what is the value inside? 11. Then finish. So only the red color need to be similar if you run using your Visual Studio. In front of this might be you get like F, 40, whatever numbers, it doesn't matter. Because the things that red color should be similar because it is depend on your program there. If you have any question, you just stop me, okay? So here, this is the explanation from previous example here, example 8. You can see just now you got the ESI plus 1. For ESI plus 1, so you're going to add 4004 because your ESI is 4004, you plus 1. So you go to the next. Then this is the answer. Okay, let's take a look another example so you can get more understand. There is no dot data. Did it refer to previous one? I think so because this value is similar. Yes, but it's okay. Later on we refer back. Now you can see here, it will be from the previous example. First of all, we move this value to our EBX. This is direct value of your operand directly inside your EBX. So this is the first value. After that, you have the EBX value at this address. You were given, it's not referred to the previous. You were given with this table. Okay, at this address, what is the value inside? Because I already mentioned this is indirect, so you're going to look into the address of this value of here. Okay, then this is the offset value. This is your operand. So you're going to tag this to your DL, to your register. But if your DL is EDL, means that you tag this and this. This depends also on the size. Finish for this side. Increase your EBX. Increase means you're going to add 1. Increase 1 je, okay? You're going to add or increase 1 only. There is no such things that you're going to directly increase to 10. No, it's going to increase EBX. So you increase and you're going to add 1. Now what is the value of your EBX? 404001. Next is move CL. Similar also like this. You need to look into the value of this. Then you check what is the operand value inside. So now it is here, right? So what is the value? It is 55. You put in your CL. So this is the 55 hexadecimal. Okay, any question? I think it is like direct direct question unless you understand the basic and you did many time on the example, just changing the value, change the offset, then you can get more understand. Okay, next we have displacement addressing. Displacement addressing, why you need to have the displacement addressing? Because it's a very powerful mode addressing, combine capability, blah blah blah. So how basically the displacement addressings look like? That is the first things that normally a programmer need to know. You can read by yourself on this, the advantages of the displacement addressing. And by using this displacement addressing, you can also having the 3 common displacing addressing technique: relative addressing, base register addressing, and index addressing. That's why later on you're going to look into one by one. First of all, what you have? Relative addressing. So let's take a look on relative addressing. It also called as PC relative addressing, which means that you're going to have a correlation with your program counter. So when you talk about program counter, normally we're going to play around with our counter at register. So this is the example of displacement addressing. This one again you already done in the beginning. This is a machine's program. Of course you're not going to understand it, but this one is offset. This one is the machines only understand. This is the program that you are programmer understand. Okay, from here move ECX 0. What is ECX? When you play around with counter and you still remember about register, you already learned C is accumulative counter register. A is accumulative, B is base, C is counter register. So you will play around with count. So first of all, initially it's going to give you ECX equal to 0. But I do believe this example is wrong. You cannot start counter with 0. Because you're going to have at least 1 to loop. If you are having 0, you cannot even loop. Okay, you cannot even loop. So your looping here is depending on your counter value. If you have like ECX2, so you're going to loop and it will deduct 1. And then you're going to loop again, it will be 1. Then you will go to the exit. You cannot just always forever looping because you have a counter. When your counter is reached to 0, which is basically 1, 1 is just one time looping, and you're going to go to the exit. That's why later on you meet for this last statement out of this looping, just to make sure that this one is wrong. Okay, but the things here, you need to go to the L1 after you have this statement, loop L1. So from here, you're going to see you replace your address from 000037. Then you replace and go to the 00028. What else? Okay, from here, you also will have what is your source and also your target following this equation, okay? Following this equation, you're going to have your destination equal to target minus source. Basically, you want to find your target, which is destination, plus your source. Then, if you already have your source address, you have your target address, then you can find your destination address. So again, over here you can see where you're going to go at the last. From here we have our target, which is L1. Our target will be L1 is equal to 28. And about the PC, this one, I think this is also wrong. Today, just today, all of the lecturers try to recorrect this slide. I don't know whether some of other sections already recorrect or not, but just today, they discuss with this, there is a wrong statement. Okay, so here, your source supposedly is going to be the end of your addresses. And you're going to find your destination. Supposedly, source will be here. And your destination will be your 28. But some things that happen here in the slide, later on I will recorrect, okay? I want others lecturer to discuss first related to this, but this one cannot happen. You cannot have the count ECX equal to 0. If not, you cannot do a looping. You go directly to exit. Okay, we go directly first to the best register addressing, EA equal to A plus R. A is displacement, R is pointer for the base address, and R also may be explicit or implicit. You were given with the program, and this is the base addressing. Base indirect addressing. You're going to replace your address for the value given on the base register address. Okay, based on the register. This is a register. What is the answer here? First of all, banyaknya. First of all, you have the D word. Let's be directly, no need for me to draw, okay? Move ESI offset array 1. So array 1, alamak, they're not going to give the value. Let me see the answer first. Okay, we still start using a similar. So array 1, I need to know, we start here with 40000. 40, silap. 404000. Okay, again in question it will give you the first starting. So here count will start first, and you're going to have the words, means until 404003. Array 1 will start at 40404. So this will be your ESI value. Again, please make sure complete the size. After that, move this value, this is to direct, EBX equal to 10000000 hexadecimal. This offset is not hexadecimal, okay, but I don't know, sometimes the question give you hexa at the end, but it is not the hexa. This is just offset and addressing. What else? Okay, next we have here move AX. You're going to point to the EBX. Where? Not. Hello? Yeah. Email apa? Tak payahlah seremoni. Woi. Woi, Iqbal. Ni ada ni. Ha. Betul. Kita orang send, Jacob tarik sign dulu. Tak kisahlah, kita bagi by email Jacob. Tak boleh, hard copy dia orang lah. Habis tu nanti aku kena hantar ke Jacob ke? Aku sudah tengah ajar ni kejap. Okay, sorry. Mana saya ambil pen? Okay, over here you can see PTR, which is point to a pointer. You're going to have EBX plus ESI. So this is ESI value. What is your ESI value? Blah, blah, blah. And you're going to have your EBX value 00010 hexa. So from here you can see this is word. This is word because you are having only 16 bit. You cannot have more than 16 bits. That's why it's already mentioned directly. If you cannot, if you did not put here, sometimes the value inside is much larger, so it's going to get error. So from here, let's say, again, I mentioned for this ESI, the value is offset. It's supposedly not hexadecimal for the offset, but when you put into your register, so you need to have the hexadecimal in your memory. Where is it? Okay, pointer, this is the value 14. Last time we did together all the lecturer and we need to draw. But it's okay, I just put the value. This one is 4004 4005 4006 4007. Ini kat mula dekat mana ya Allah? 4000 40001 40002 40003. After that, over here we continue. We start with 40004 40005 40006 40007. Here we have the value of 40008 and 4009. Here we are having the 400A, 400 which is 10, 40011, 40012, 40013, 40014. It's going to be long, okay? 4000 4015 until 1 2 16 15 16 17 18 19 20 21 22. Okay, this is the addresses that you have. You can draw by yourself the stack, how it look like. So basically at 4014, where is it? 014. The offset, I did wrong. 14, my calculation is wrong. Okay, supposedly your 4014, it is supposedly at here, 4014. You need to make sure that this is not hexadecimal. Okay, this is not hexadecimal and this is hexadecimal for the value of offset and the value of your EBX. Because this one EBX plus ESI. This is 10. 10 convert to your decimal, please. 10 convert to your decimal. And then you just add on with 4004. How much?
10 hex betul. So convert to decimal 16.
16. Okay.
Yeah.
You're going to have 0040404020. So this is the addresses that you supposedly tag the value of your AX. So your AX just now, so I am correct. I'm starting from, supposedly here is 4020. Okay, 4020, 4021. Might be I miss 1, 2, 3, 4, 7, 8, 9, 10, 11, 12, 13. Oh, this one ada lagi. 14, 15, 13, 18, 19, 20. Correct. Correct. Okay, this one is correct. 4007. This one is 4008, 4009, 40010, 40011, 400 berapa? 12, 400, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, because this is the word. 20, 21, 22, 23. Okay, this is the final address. So your offset here, if you run, okay, might be I have a time, okay, I can copy this, I can run to Visual Studio. Okay, you're going to have the AX value by adding these two. This is hexadecimal. When you convert to decimal, you're going to get 16. You add, you're going to have 4020. And that's why at 4020, it is 8, 9, and 402167. Okay, you cannot basically directly add on together. This one is wrong. This offset. Sekali dia nak letak mana? Directly adding. And again, I mentioned, normally I was like questioning. Here, the value is known as a offset. So offset, supposedly when you have the value of offset, offset is not hexadecimal. But the direct value here, 10 hexadecimal, is hexadecimal. When you want to adding it together, you need to convert it to decimal. So you will get this one, you convert to decimal. This one, you convert to decimal. You will get 404020. So point at this addressing 402021. So you will get the value of 67. I already run this statement, this program, and then I get the similar answer. If you try to run, you also will get the similar answer because of that is a hexadecimal. Mana I punya slide tadi? Example. Okay, I copy this. Okay. Data until n. Okay, I copy first back ah. Where is my line? Why I cannot run and paste? Okay, this is my Visual Studio. You can see here, I just copy similar program. I copy the similar program and I want to see the output of my AX. Okay, I want to see the output of my AX, the red color one. So let's see what happened. From here, I can like directly go and get the answer. This is my answer. 6, 7, 8, 9. You can see here? 6, 7, 8, 9. You can try to do also one by one. Okay, where is my pointer? F10. Okay, now I have one by one. I can see also what is the output. Tapi besar sangat. Mana my output goes? Wait. Windows. Salah tekan. Register. Kenapa dia besar sangat? Okay, this is my initial value for my register. So I step over another one more time. You can see what is happening. My ESI value will be changing and I'm going to follow the value of offset array. It doesn't give me initial value of these things. That's why my array 1 and your array 1 sometimes is different. Again, okay, sebab it is depend on your machine address. It's directly see where your address of E1, count 1 starting. It doesn't mention in the program, so it's depend on the offset of your array 1. Now my array 1, your ESI is 0040604. You can see here, it is not similar. ESI. Because normally in question, we will give you the offset value. But it's okay as long as you understand. After that, you're going to do putting the EBX. EBX, we're going to see all of these size will be occupied. I step over again. I'm going to pick the EBX value. EBX, where is my EBX? Here, and I'm going to add with my ESI value now. And supposedly, because you already start and your stack is similar, starting at which pointer, then you will have the value of similar things. This is your AX, only this one. In front is not your AX, because your AX only 16-bit. Okay, your AX is 16-bit. Please try to draw your stack and try to see carefully until you get 4020 here. If you do one by one, then you will get. Okay, this one is wrong. Okay, this one 4016 4014 is wrong. And what else? Okay, you can try to run this. We go to the slide. After that, after we done this, we're going to pick the ESI value directly to our adding this value, adding with our EBX. So when we add this, we just directly adding. After that, we have the move value. We can try to run our ESI now. Here 6004. Let me try to 6004. And our kenapa question saya lain? Adding, okay, betul lah. Adding EBX. EBX is 10. Okay. Step over. So I already step over and I'm going to see my EBX value now is 406014. Just adding directly from the value previously. 10 with 6004. Okay, but this one is only applied when you are having register with register. But when you go for the pointer or offset. Pointer or offset is not hexadecimal. This supposedly value of decimal. That's why you need to change just now tens to be the hexadecimal to be decimal. Then you will get 4020. Next here, last one is also similar, but now you just having the EBX value. EBX now is already updated 4016. So at 4016 here, I think this one is also wrong. Let me try to run here, okay? F10. Okay, for F10, our CX, where is CX? 67. So from here, you're going to see, might be you try to do, I'm going to convert, okay, for hexadecimal. 4014. You put inside here. This one is supposedly in the value of decimal. Where is decimal? Hexadecimal to decimal converter. What is the value? Four zero 20. Supposedly it is going to be 20 in decimal for the 14. So that's why you will take the 14 which is 67 and 89. But
Better.
yes.
Sorry, you all stop sharing.
Okay, wait. Okay, here you are having the 14 value for the EBX. When you convert here, you're going to get 20. Supposedly, it's going to be 20. 404020. But I don't know what is going on. It's here. It's directly pick the 40414. You look into the answer here. You're going to pick the answer of 6789. When you do one by one for the size, then you will get it at 20. So supposedly hexadecimal. Okay, I will double check. I will redraw back about the stack. I hope that you can try also to draw back the stack and check the answer. But totally this one is similar in the output. You can try to run also in the Visual Studio. I already try and it get the similar answer. Is there any example? No, this one is also exercise. Wait, exercise here. Where is the pages? Okay, this one is also exercise. Supposedly it's going to be similar to just now. But you can see this beginning of offset already given. So it's quite similar to the previous answer example. So please try to do and run also. Later on, I will draw mine carefully at a piece of paper and I'm going to share with you how the stack will be look like. This one got count. For the example, there is no count, I think. Yeah, it's direct to the array. Okay, I think only that for today. Later on, we will continue, but the next is not too many. So I will finish this with another just in a video. Later on, after Raya, we'll directly go to our module 5. Is it okay? So module 5 is more on theory also. A lot of theory. But there is also some things that you need to know in terms of, I don't know, this is not calculation, but your understanding with the numbering, especially on the addressing and the value. Okay? Any question for now? I need to double check where is the COE lecture group. Okay, if there is no question, thank you everyone. Selamat Hari Raya. Stay safe. Meet you again. I hope that next class we're going to do also a lab for this subject. We don't have face-to-face. We got face-to-face, right? Hybrid class. So I hope I can see you in UTM. Okay? Bye-bye. Assalamualaikum.